Okay, so let us look at energy in building. Now, there the operating in building operating energy is the major contributor. Operating energy is the major contributor, right. How? Let us see. This depends upon environmental temperature, relative humidity, solar radiation, that is what we have seen. That is what we have seen. Some of you may not have taken that course, but generally it would depend upon the environment, thermal comfort of the people. For example, this room is maintained maybe at about 25 degrees centigrade or something like that, 25 degrees centigrade, that is what it should be normally. Some other places it might be 20 degrees centigrade. So, today of course, outside is all cool, but in summer time it will have higher temperature outside, solar radiation falling onto it. So, you have ways and means of calculating this. We might look into some of them or may not, we will see that. So, operating energy depends upon environmental temperature, outside relative humidity and solar radiation, because relative humidity is important, thermal comfort depends upon relative humidity. If you can recollect, we have seen that there are 4 factors which governs the thermal comfort. If you recollect something like TSI, tropical summer index, just for your recollection, those who have done a course on building science would know this is one of the comfort index, and comfort index means what you do, I club temperature, relative humidity, air velocity, and of course, if there is a radiation coming from the wall, etc., that also I take into account. So, tropical summer index is given by some K1 temperature, what we call dry bulb temperature, plus K2 wet bulb temperature minus some K3 into root over velocity, right, something like this. I just deliberately did not give you the equations, this is 3/4, this is 1/3, etc., and this is 2. So, roughly some of those who have done those courses, they would remember. This is, so the point that I am trying to make is, it is a function of temperature. Now, dry bulb temperature is temperature of the normal thermometer, as you understand, right. In the room, if I put a thermometer or some sensing devices, sensible heat sensing devices. The second thing is, if I in a thermometer, if its bulb is kept wet by gunny bags, I mean jutes or something of that kind, kept it wet, then temperature will come down because of the evaporation. That we call as wet bulb temperature, right. So, that depends upon relative humidity. If the relative humidity is 100%, there will be dry bulb temperature and wet bulb temperature will be same, because there will be no evaporation. And if the relative humidity is very low, lot of evaporation. So, difference between TD and TW will be large. The point that I am trying to make is, and if air passes through your body, some heat will be taken away. So, in summer tropical summer index, as I am calling it, these are all function of dry bulb temperature, wet bulb temperature, that is relative humidity, and air velocity as well. So, this will depend upon those situations, this will depend upon all that. So, if you have change in temperature, supposing there is a change in global warming and change in temperature, this will in fact will have a cascading effect on the energy use, right, would have a cascading effect on building energy use, because higher temperature, particularly in tropical countries where temperature is higher. So, therefore, you would need more energy to be removed. So, this is called as kind of a cascading effect, vicious effect in fact. So, therefore, minimizing of this impact would better, so therefore, you need to control this as well. Minimization of the impact would require better control of envelope and equipment through greener materials and technology. So, basically, which is responsible, what is responsible for this energy? We have seen this relative humidity, temperature and air velocity within the room, but if I have outside scenario, if I look at it, I will have some temperature, of course, some relative humidity and RH outside, and then if I put a notation TO, RH outside, and solar radiation that is received, intensity of solar radiation that is received onto the building. Now, if this is my building, outside conditions are this, then heat flows, in summer condition heat flows. So, higher this temperature, more heat will come inside. So, thermal comfort will be disturbed, and if I am keeping and doing if it is a conditioned building, trying to maintain it comfortable temperature, more energy need to be withdrawn, more energy need to be withdrawn. So, therefore, this this, and who controls this? The passive part. Active part is one which in a building, even in structural engineering we talk of active and passive part, earthquake engineering. Active part is one where I give some energy. Passive part is which is part of the building itself. Passive part is part of the building itself. In the of course transportation system, most of it is passive. The example is, say, structural system, you have active systems for earthquake engineering. In buildings, a sprinkler is an active system, partly active system, not fully, although energy consumption is less, so we do not really take it. Sprinkler means what it would do? As soon as the fire is there, it would be detected and it will start sprinkling the water onto it. So, therefore, that is more of an kind of an like energies depending upon how much energy. Air conditioner is an active system because it actively withdraws, but then passive ones are the walls, the envelope, that is what I was mentioning. The envelope of the building, envelope is just around surrounding building and its surrounding area. Maybe I will have a formal definition in the next class. So, envelope is the one which controls the, is a passive part which controls the energy coming in. So, your first thing is envelope design should be such that, and as we shall see, look into lead rating, envelope plays a big role there also, is a possibly major one of the major thing. Then the machines that you would be using, right. So, that is what I am being said here, minimization of control of envelope in building, design it in such a manner that heat flow is minimum, and equipments, so air conditioning equipment, right, active systems, active ones, through greener materials and technology. For example, a simple thing is the lamps today. If you look at incandescent lamp which we were using earlier, maybe almost from the time of Thomas Alva Edison, who invented that, right. So, those lamps was consuming very high amount of energy. The lumen output was much less. Lumen is the unit of light, right, and lumen output per watt or was much less. So, you would have needed a 40 watt lamp, then the technology improved in over last 10-15 years, and the kind of LED light which you use, the same the lumen output you are getting from a 40 watt lamp, you might get from simply 5 watt or 12 watt, 7 watt or 8 watt or something of that kind. So, the you see equipment efficiency, I mean this is just an example, equipment efficiency, you must see that if equipment becomes efficient and you use a more efficient one. So, that is what it is. So, the two cases you can see, this is some case studies, real building in Chennai. Now, these two cases, I suppose this is one of those Ascendas building or something of that kind, close to IITM. Two buildings, one can model them and look at the, one can calculate out the embodied energy of building. Some guidelines I will give you how to calculate, but unfortunate part is we do not have data available in Indian scenario. Data of embodied energy of materials, because the transportation energy will differ from country to country. Production energy, depending upon efficiency of the production, it will differ from country to country. UK they have complete data has been given in one of they are in the website, possibly some extract from that I have. So one has to go to the site, actually do an accounting of the energy being used up in production of everything, and that is how you should be able to find out, there is no other way. So, the original raw data in India is very limited, there is small data, I will give you that later on. But based on that or whatever is available, one can calculate for the whole building envelope material, embodied energy. So, roof slab you can see it contributes this much. Glass, that contributes this much. Floor slabs, because number of stories in the building, you can see that many stories in the building. So, number of floors are more. So, therefore, totally on the floor slabs, it is only looking at the building envelope material, floor slab and concrete wall. So, this is the concrete wall. So, component wise it is seen, embodied energy in megajoules is something like this. And if you see the second building, well, second building will have a similar sort of thing, and if you see their operational energy, that will be much larger. I will come to this later on. Yeah, embodied energy of the building B, again something like this. So, the floors, those are there because they are the, if you look at the concrete system, that would be majority, roof, etc., etc., depending upon how much glass you have, glass can contribute to them, exterior wall can contribute to them, right. Now, energy consumed during the life of the building, one can calculate it out this way, because if you, this can be simulated in, this you can simulate in software like Equest. Some of you might be familiar with this name. There are open source software available for calculating building energy, right. So, you can model them, model the building. In fact, this building was modeled for, these are models for use in Equest. These are model for use in Equest. Energy Plus, which is of course not open source, but there are Ecotech, there are several such softwares available today which one can use for calculating out the energy consumption. Of course, we have in one of our earlier courses we discussed about the methodology, the equations and things like that, heat transfer in building and so on. Those who have taken that course, they will know the basics, fundamental behind this, but softwares are very robust, they can calculate for any building. So, using those softwares one can calculate out the energy, right, and this is the cumulative energy, operational energy, right, for building A. So, you can see since it is over the large number during the 50-year cycle, complete 50 years, total quantity of operational energy is much higher. Embodied energy is once you have done without assuming any repair in this work, repair was not assumed, it remains same. This is in Infotech building actually in Chennai and Ascendas building in Chennai, both are close to IITM, and embodied energy is fixed because it is not going to change unless you take the repair. So, this is a major component, and if you are trying to make your building green, then you must address this issue in much bigger way, right. Okay. So, let us go to this is a UN United Nations, I think it comes from zones 1988. This is from UNEP source. This gives you years and this gives you the embodied energy, total energy. So, embodied energy is somewhere here. There is some amount of grey energy. The grey energy is related to energy of repair, which is not easy to quantify, but some idea. So, other sources of energy which are not measured, but look at the operating energy which is going from here to straight away up to this, right. So, these lines are actually demarcating, this lines demarcating, and after demolition you might recover something, right. After demolition also you might recover. So, demolition because recycled. So, accounting if you are doing that, if you have recycled the energy that you would have used in producing that, right. So, operating energy is significantly large, operating energy is significantly large. So, we should this is global, I mean from this sources. So, therefore, this is true for any place. So, both embodied energy and that is what we were talking of life cycle energy. So, one should actually address the question of life cycle energy, and if you are able to address even the question of grey energy, for example, if you do less maintenance, no repair, if you do not replace your, let us say you have used an insulation system and it lasts for 60 years, obviously grey energy contribution will be less, but if it lasts for 20 years then it will, you have to replace it 3 times. That means, the embodied energy now you added 2 more times, first time you added, second time, third time, because you have replaced it twice in between, and 60 years obviously you may have, I mean you may not, you can't plan for more than that planning horizon. You would have in engineering economics you would have come across when you do, you have 2 projects you want to compare, you you have what is called planning horizons. So, buildings normally our planning horizon is 60 years. So, if you are doing twice repair, your grey energy is more and so on. So, that is what the importance of this one is. Yeah. So, typically if you see that when we look at the lead rating or similar sort of rating like Griha, lead rating is one of the which we will discuss it somewhat at slightly more length. It started in United States actually, leadership in energy and environmental design, right. So, they give rating based depending upon your features of various features of building, starting from site to the site to everything else. Insulation plays a big role there. So, what we see is these two buildings, if you see, if you take at different climates, Chennai, New Delhi, Jodhpur and Bangalore, same building, those two buildings, right. It is one building B, which was that Ascendas building, second building I talked about. If the same building was to be built in, let us say New Delhi, it is actually in Chennai, its percentage of energy saving that you get from the base case, if you improve the insulation from whatever was existing. So, you see that it improves, right. Blue one is New Delhi, higher the insulation, energy saving increases, but does not increase beyond a point, of course, to a higher rate. Now, purpose of selecting these 4 cities were also, there is a purpose. What is the purpose? The green is Chennai, okay, where it is. Now, that climate we call it warm humid climate. So, some of you are familiar with this because already we talked about this. Now, what is warm humid climate? A warm humid climate is classified by high humidity. Without going into details of this, because then it will be repetition with another course. So, I am not doing that, but those who have not gone, for them a little bit. High humidity is characterized by high humidity throughout the year. Low diurnal variation means temperature, day and night temperature variation is lower. So, variation of day and night temperature, night temperature, diurnal temperature variation is low. Delhi if you see, or Jodhpur if you see, summer Delhi minimum temperature goes to around 25 or so, maximum will be 45. So, could be even higher, right. And Kabul is all low, it is lower temperature, subtropical.
Goes to minus also,
Yeah,
like minus 10.
So that's Addis Ababa is like Bengaluru, does not change much temperature. They are in the equatorial plane and somewhat altitude, so therefore that does not change. But so warm humid climate is where humidity is high, right? Humidity is high and diurnal variation is low. Maximum temperature is also, annual maximum is also low. Annual maximum is also low. So, Chennai is that kind of climate, while Bengaluru is one where temperature variation is more or less much low variation, is almost like subtropical climate, it's all different climate basically. So, you do not have to, here the temperature variation is low, humidity variation is low, relatively comfortable scenario all the time. And if you look at Jodhpur, which is hot dry desert climate, what is the latitude of Kabul?
32.
Almost like Srinagar, yeah. So, this is along that, almost along that line, therefore, that summer temperature also goes high up relatively. So, anyway, Jodhpur is desert like, where the temperature variation is very high, winter temperature also relatively goes low. So, that is why these 4 cities were selected, and in all cases what you find is that as you increase the insulation, obviously Bengaluru will have less effect because it is more or less comfortable scenario, So, as you increase, there is an increase beyond this point, really it may not have much of a benefit, but that is what the point shows. So, let us look at life cycle energy of the building. Maybe we will see it a little bit more elaborately later on, sometime again a little bit. So, if you see up to this portion, this is the life cycle energy in building. Whole thing is, I think is visible properly, or this is the whole thing we are looking at, the life cycle energy of the building. This is building materials embodied energy, right, and building materials embodied energy, and this is operational energy. This is operational energy. It is only showing the component of embodied energy and component of operational energy. This is not percentage. These are not percentage. It is not that embodied energy is much more than operational energy. Now, what does building operational energy constitute of? Heating and cooling. Heating, cooling, lighting and ventilation, lighting and ventilation. Then appliances, operating appliances, right, for example lift, right, lift or any other household or common everything, other building related energy use. So, main is obviously heating, cooling, lighting, ventilation, and then all appliances and so on. And if you come to this will have some direct energy. For example, if I start from here, note the demolition, construction and assembly at site. First is the material, then construction and assembly at site, prefabrication activities if it is required, transportation to site and off site, and some energy might be spent in administration and things like that. So, initial embodied energy, then upstream processes, if you look at it, raw material production, then main processes, and then downstream processes. So, for example, upstream processes like I was talking about cement production. So, raw material to handling the raw material, producing processing them, that raw material extraction, that is basically upstream processes, and then transformation, this material from raw material to cement, this will be one, and then cement to concrete and to building element, everything has to be there. So, that is what it is. Then main processes, right, making concrete, then transportation. So, some of them, then additional will be renovation, refurbishment, maintenance, etc., that will have energy also involved, that forms a grey energy kind of thing. So, then initial embodied energy is this, recurrent embodied energy from the renovation and refurbishment and things like that, and demolition if there is some energy spent on demolition, that is what it is. So, this is actually this shows the total life cycle energy in building, and one have to address this, one has to address this. How can you do this analysis? It is not easy to do, not a very complicated mathematics or anything of that kind, but it is a laborious process. So, if you have, for example, if I want to find out how much is the energy, embodied energy of cement, then first the steps are too many. So, possibly you have to find out the machinery which actually crushes the rock at the site, how much energy it consumes, fuel it consumed per day and produce how much tons, right. Then there will be dumper trucks which will bring this quarried material to the crusher. So, a dumper's capacity and how much distance it travelled, which you may have to average of, right, or if it has gone to for homogenization, somewhere it has been placed and some scraper or cranes they have used to homogenize this, take raw material from one place to another place, mix them together to make it all homogeneous production raw material. So, you have to actually go take those data has to be generated in that manner. So, it is not going to be easy, and then it comes to the crusher. So, sizes, as the sizes increases, sizes becomes finer and finer, energy required is more. We will see that sometime later on, grinding energy or crushing energy. So, calculating this out, how can calculate? You have to find out the fuel consumed, if it is electricity, how much electricity consumed in the crusher, any other somewhere the fuel that will be used by trucks. So, this becomes a very laborious process, but some people have done it anyway. So, statistical analysis, the industry might have done it, the total energy you have used in fuel for this much ton of cement production in the year is this, because this accounting would be available. So, without going to each individual ones, I mean individuals one will be important if they are trying to reduce it, trying to find out where it is high and you want to cut it down. But overall, if they want to find out if for third parties purpose, then total from the published data of the industry one can look into. Then input analysis, that is what I was saying, relies on economic input and output of the nation. Okay, for the nation also one can look into money flow from energy producer to the each sector of energy. So, that is very bulk way, and from that also one can get into how much is the energy. Then process systematic examination of the direct and indirect energy input to the process, this is high effort, that is what I was saying in the beginning first, then statistical, and then the third is the nation wise electricity boards or similar authorities which supply the electricity, how much energy they have supplied to a particular plant per annum. So, there are different ways one can actually look into this to find out what type of energy has been given to what production, how much cement they have produced and so on. So, that one can find out, and actually one can use combination of that. So, this is not this definitely effort required, and it is not a very great work, but a lot of hard work required. So, life cycle energy implication is very important, greenhouse gas contribution is very important, contribution to natural resources and depletion of natural resources other than those used in fossil fuel, so natural resource fossil fuel is already will be taking into account separately, but other than like he was talking about recycled aggregates in cement, concrete, or if you are using alluvial clay for production of clay bricks. So, you are using those resources. So, how much is that one can find out. So, sustainability performance shall account for all, it should take account of all these issues, and in terms of life cycle, right, in terms of life cycle. So, that is what it is. Primary energy source you cannot produce, it is convertible, efficient process will use least primary energy, work, okay, this is fine, this I will not talk. So, work potential is measured in terms of something called Exergy, which we might touch upon sometime, is a theoretical work obtainable from a stable system which is brought to equilibrium with the surrounding environment. This is a terminology used in thermodynamics. This is a maximum theoretical work you can get. Energy is one issue, but energy whenever you are converting or using into work, there is a loss. This looks into the actual work that you are able to do, the theoretical work that is possible from a which is brought to equilibrium with the surrounding environment. So, that is what is the work potential, that is what it looks into, and when one is trying to make the process efficient, let us say cement plants, for them it would be very useful. They should see that how they improve the exergetic efficiency, as we call it, energetic as opposed to energetic efficiency. We may not discuss this too much. Energy is never destroyed, but work potential is destroyed, work potential is lost, right. Energy is never destroyed, this is irreversible, exergy is destroyed, right. Okay. Yeah, this is a little bit fast, this fast. Energy incorporates all natural resources. Exergy can incorporate all natural resources consumed and can combine resource depletion, energy consumption, etc., but I do not think at the moment we have a theoretical model to do that. So, can combine both fuel and non-fuel materials, so using Exergy, the work potential you can actually combine, or all the processes can be combined. So, look at this for coal. Mines, I have got 100% work potential, right, 100%. Then I have extracted it, I have spent some energy onto it. So, this much energy I have spent, now it is effectively accounting wise 94% after extraction. And then I might have done some enrichment, that means I might have washed it, right, to remove the clay, some enrichment I have done. So, another 10% gone, and 87% because I would have transported it, delivered somewhere. And then as I produce steam, the effective work potential of the steam is 44%, right, turbine, steam turbine I was using. And then power generation from the steam, there is some amount of loss here. So, work that the power that can do, power that I have generated can do is only 33% of the that was available with the in the coal, right, and then finally available for consumption. So, therefore, there are a lot of work potential loss at every time, and final I get much smaller than what I should be actually originally was there in the mines or in the resource or wherever it is. So, I think that finishes any discussions. We can take some questions if you have.